Okay, let's check these practice questions out. So with the first one, we're saying a particle with a charge negative q is located at a distance d from a particle with a charge positive 2q as shown in the figure below. Which of the following best describes the location of a point other than infinity at which the net electric field created by the two charges is equal to 0? So when we're doing electric field, we're going to think about what would happen if we brought a little positive test charge in there. So if we brought a positive test charge next to this negative q, this being our source charge for the moment, we know that it would be attracted to it. We would have this little arrows going towards it. The positive test charge would be attracted to this positive or this negative q. If we think about this one, this positive 2q, if we were going to bring a positive test charge over here, the positive test charge would be repelled. It would go away from it. So we would need to find some sort of point, and let me kind of extend these just a little bit. Get a little bit weaker. Same thing. Still exist. Just getting a little bit weaker. Weaker. And then same thing with these guys. They're going like this. And they're going to get weaker. Further away. But they are. Okay, so if we're looking at these, which region could we have this cancellation? So in this middle region, D, everything's pointing the same direction. Everything's going to the left. So this one seems like a no-no. This seems not good. Region 2, I don't believe so. Region 3, we have a very strong electric field from this 2q charge because it's kind of right directly next to it. We know that electric field is going to fall off with r squared. So over here we have a pretty strong electric field that's pointing to the right. And yes, this region 2, this negative q, will be pointing to the left over there, but it's going to be pretty weak because it's pretty far away. So that'll be pretty weak, so we probably won't get that, we won't be able to cancel it out. Region 1 seems like a pretty good candidate. Region 1, we have a q over here, and it's, just regular q instead of 2q. So it'll be not very strong, or not as strong. This 2q will be a little bit stronger. So when we get over here, we will have them pointing to the left, but they'll be a little bit stronger and maybe strong enough to cancel out the rightwards field from this negative q. That would be region 1. All right, with this one, the figure below shows lines of equal electric potential in a region of space in the plane of the page, at which labeled point is the magnitude of the electric field the greatest. So when we're looking at this, we can think about these as topographic maps. So if we look at them, if we kind of think about topographic maps, or just maps in general, if we have kind of this really shallow ascent, we have like kind of pretty spaced out isolines. They're very spaced out. It's kind of a rough drawing, but that's okay. They're very spaced out. Maybe I should do circles. If we have these isolines that are spaced out, whatever. If they're spaced out, there's not that big of a change in energy. There's not that much force acting on them. The field's not acting as strongly. But if we have these really tightly packed isolines, that's kind of like a steep ascent. That's kind of like, hey, we have this large hill. So A, we have this really tightly packed isoline that's moving through a large amount of potential. So this is going to be where our field is the greatest because this is where our isolines are more tightly packed. So we're going to have the greatest field at A. So over here, this is weak, pretty weak because they're all spread out. So we don't really have as much of a change in energy, but through A, we have this large change in energy, which means that we have a greater field. All right, the figure below is showing us, okay, this doesn't really matter, whatever. We have a uniform electric field. We're going to say when we move it from one point to the other, how does this potential change? So VRS is just going from R to S. ST is going from S to T. TU is going from T to U. And then RU is going from R to U. And we want to know how do these potentials compare to each other. So if we look at it, we have, here's the direction of our electric field. And then that means that our isolines are going to be perpendicular to that. So we just have these perpendicular isolines. And we don't really know the direct voltages, so we can just kind of draw in general isolines, I suppose. That's a whatever. So we can just draw in these isolines, just draw them equally. And we would be able to split them up if we actually knew values, but we don't, but it doesn't really matter. So if we go from R to U, that looks like we're moving to the same isoline as going from S to U. So we can say that VRU is going to be the same as VSU, because it doesn't really matter if we move across these isolines. We said that that's free. That doesn't take any energy because we haven't changed the potential. So that doesn't change anything in terms of energy. So VRU, even though R, we have to move down a little bit, that's free. That doesn't matter because we're at the same potential. But if we move across, that is changing our potential. So RU is going to have to equal SU. Do we have an option like that?